Okay, so we've done some differential equation work in the first part of this section here up to example 9, using what we call the separating variable separable method. And that's when we're trying to separate the two functions in x and y on either side with dx and dy in the appropriate places. It's not always possible to arrange a first order equation like that, and therefore we need another technique. So here we have a second technique for solving first order differential equations using the integrating factor, and we use that when we find an equation in this form here, when we've got a derivative dy by dx added to that some function multiplied by the original function y equal to some function in x. We can't rearrange that even if you wanted to try. You couldn't rearrange that in a way in which we could use the separating variables technique. So we need a different way. And so what I'm going to do is very briefly try to show you the background, the proof of why we use a couple of equations we're going to use. Basically, you're going to come up with a couple of formulas that will help you solve the rest of them. But at the moment, I'm going to effectively prove why we use them. Okay, so what we do is we're going to introduce this integrating factor mu, and that's the symbol for mu here, a little Greek symbol mu. Mu of x is a function in x. Okay, so we multiply everything by mu. We end up with mu of x dy by dx plus, now I'm going to say p of x mu y equals mu of x times q of x. Now, the left-hand side, and this is where it gets a bit interesting, this bit here looks kind of like it's the product rule. So we've got a sum of terms, yep, and we've got on the on one side we've got dy by dx and y, so we've got y and its derivative, and it would work if this mu of x here, and this, so in other words, if that was the derivative of this, if these were related to each other, then we would have a product rule. Okay, so what we want to do is to choose such values such that, if I see if you can get this, that we want that to be mu of x, the derivative of mu of x would be p of x mu of x. Okay, and that would then be in the shape of the product rule. In other words, what we want to do is choose such a value that the derivative of mu of x is equal to p of x mu of x. Okay, and we can see here that the derivative of, what we'd have to do, we want to maybe see if we divide through by mu of x, is p of x. Okay, and if you have a look at the left-hand side of this here, here's another shape here. If the derivative of mu of x times 1 over mu of x, well, actually, that looks a bit familiar. That's effectively, if we were to say that the log of mu of x, okay, the log of mu of x would be, if we were to differentiate the log mu of x, we would get 1 over mu of x times the derivative of mu of x. Okay, let's just check and see. If we were to differentiate the log of mu of x, that would give us 1 over mu of x multiplied by the derivative of mu of x, which is exactly what we've got here highlighted in yellow. So what we're saying is that that could be the derivative of log of mu of x, and that's the chain rule stuff going on. And so we can say that all of these are then equivalent to each other. And if the derivative of the log mu of x, if we integrate both sides, we get the log of mu of x is equal to the exponential to the power p of x. So we're integrating both sides. No, in fact, that's not yet. We're integrating both sides with respect to x, and then we want to raise both sides to an exponent of e, which would be that e to the log mu of x is e to the integral of p of x dx, and of course that allows us to state that the value of mu of x that we want to choose is e to the power of the integral of p of x with respect to x. And that is our formula that we're going to use. Okay? First formula to find the integrating factor. You don't need to kind of prove that. Somebody a while back sat and thought, oh, that's a good way, that the left-hand side here looks a bit like the product rule, so if we set values and we manipulate that, then that's going to help us to come up with a value. So now we can say that if we, from what we had, remember we multiplied everything, mu of x dy by dx plus p of x mu of x y equals mu of x q of x. That was what we had there. It's really on the left-hand side, because we've chosen this value of mu of x to give us the product rule. We're basically saying that, so in other words, we know that that is a derivative of that. We can then write the whole of the left-hand side as a derivative of just the term mu of x y. Let's just think about that. So if we differentiate that function, we'll get the derivative of mu of x, which is here. That we've already said that's what that should be, times y plus mu of x times the derivative of y. We've got our product rule set out, equals mu of x q of x, which means that if we integrate both sides, we get mu of x y is equal to the integral of mu of x q of x with respect to x, which means that y itself is 1 over mu of x times the integral of mu of x times q of x with respect to x. Okay? So the only things you're allowed in that final formula on the right-hand side are things that rhyme with mu and q. So if there's a p in there, then you've got that wrong. Mu of it, 1 over mu of x times mu of x q of x dx. Now that's our second formula that we're going to use. So we don't need to derive these things because we can use them as they stand, and then that will help us solve our first order differential equations. Okay, let's move on and do one then. So here's example 10. Find the general solution of the differential equation dy by dx plus y over x equals 1. So the first thing we're going to do is make sure, and this is really important, that the dy by dx term doesn't have a multiplier in front of it. It must be a unitary term, which it is in this case. That's fine. So we want to define, and it's helpful to do this first of all, define the values of p of x and q of x. So we've got here effectively 1y over x, so p of x is positive 1 over x, and q of x is just 1 just now, nice and easy. So what we can say is that the integrating factor mu of x, what did we say? It was going to be e to the power of the integral of p of x dx. Now, it's better just to deal with that at the side first of all, rather than deal with the integral in everything else. So I always tend to do this at the side. So the integral of p of x dx is the integral of 1 over x with respect to x, which is a natural log of x plus c. Now there's a plus c here which we don't use because we've got some integration to do later on, and that'll take care of it. So we're only going to use the log x bit. So mu of x is e to the power log x, which in this case happens to be just x. So mu of x, the integrating factor, is x. That means that we can actually find the general solution because we use the other formula. General solution says that y is equal to 1 over mu of x multiplied by the integral of mu of x q of x dx. We know that mu of x is 1 over x multiplied by the integral of x multiplied by q of x was just 1. So we've just got the integral of x dx, which we can go through and do. Y is equal to 1 over x. The integral of x with respect to x is x squared over 2 plus c, and therefore y is equal to, if we multiply out in by 1 over x, we end up with x over 2 and c over x. And we have to keep, this is always a case of we have to make sure that we include c in any of the multiplying out that we're doing. Now that is actually the general solution of our differential equation, and when you use the formulae, it's quite straightforward. We don't have to prove anything necessarily, but it's good to know where these different formulae come from. We'll check out example 11 and we'll keep moving through some of these different examples.